in this active circuit that is designed using two ideal op-amps, we want to show that the output current I out, the value of it is independent of ZL, and it's only defined by the input voltage V and also resistor R, not even resistor R1. So it's very interesting, and also there is a negative sign there. So by that I mean this circuit effectively converts input voltage to an output current, so hence transconductance, because transconductance means conversion of voltage to current. At the same time, this conversion has a negative coefficient, so hence negative transconductance, effectively as if we have designed a negative current source. That's very interesting. And again, the value of current is independent of load. So that's also interesting. How is this possible? Okay, so let's make the assumption that op-amps are properly biased. I mean the positive and negative supply voltages of the two op-amp 1 and 2 properly applied, so that op-amps are with the proper negative feedback are in linear region of operation. Therefore, virtual short for each op-amp is valid, and by that I mean the voltage at the positive input terminal is the same as the voltage at the negative input terminal for each op-amp. Now, that means the voltage here should be the same. Let's say the voltage here is named just as an example, VA, should be the same as the voltage here, VA. So these two voltages are the same. Therefore, I can form a KVL or loop here. So in this loop, let me put it this way. There is a current I that is flowing, and this current I goes through resistor R1 and continues, of course, going to the resistor R1, because nothing can go through the input terminal of linearly operated ideal op-amp because it has infinite input impedance, the same thing at the bottom. So the current I keeps flowing this way, the current I keeps flowing this way. But effectively, because these two nodes, they are enforced to have the same voltage, I am able to write a KVL here effectively. By KVL meaning, I can say if this is loop number 1, so I can say KVL for loop 1, I can write voltage V, and then I have, as you can see, I have an IR1 drop across the first R1 resistor on top. So V minus IR1 drop. And then I get to the voltage. Let me use a different color so that you can see it. And then I get to the voltage here, which is the same voltage here. So I get down to this point, and then I have another IR drop. So IR1 drop, because it's the same R1 resistor. So then I have another IR1 drop, and I get back to the input voltage source V. So as a result of this, I can say this I that is flowing to the left-hand side of the circuit is effectively equal to V divided by 2R1. That's the equation 1, let's say. Now, as I showed here, this current I is keep flowing through the another R1 resistor, so to get to the point that we refer to its voltage as Vx. Also at the bottom of the circuit, let's refer to the voltage at this node as Vy. Effectively, the voltage across resistor R is obviously Vx minus Vy. Okay, so how can we utilize this? Well, what is Vx minus Vy? Take a look at what's happening. It's V because it has the same, let's say, voltage directionality as V, so it's, or polarity as V, so it's V. But then let's see what's being subtracted from V. Of course, on top we have a voltage drop across. Let me use a different color so that it's clear. So we have a voltage drop across the two R1 resistors, and we have another voltage drop across the two R1 resistors at the bottom. So I can say V minus 4R1 times the current that is flowing them. I. And then I'm going to use equation 1 here to substitute for I. So V minus 4R1 divide by V divide by 2R1. So obviously what I get is V minus 2V is negative V. That's very interesting. So I found VR, or voltage across this resistor R, to be equal to negative V. The current I out is obviously defined by voltage across resistor R divided by the value of resistor, because again, no current can flow through the input terminal of ideal op-amp, because as long as it's linearly operating, that input terminal has infinite impedance. So all the I/O is coming through R and going out to ZL. So therefore, it's according to equation 2 that I just found, this equation, that VR is equal to negative V divided by R, and we are done. So I out is minus 1 over R V in, as we wanted to prove. So again, this circuit realizes a negative transconductance, and effectively we have designed a current source, a negative current source, that is controllable via the input voltage V and a resistor R as the parameter of the circuit. I hope that this is helpful.